Now, this 10 ohm 1 watt resistor has already been burnt from a previous experimentation, so let's actually destroy it completely by putting it across 15 volt uncurrent limited. See how long it lasts. Woohoo! I think we can safely say we've destroyed that resistor. Greetings, the Astro 30 here yet again with, I want to say a mini project series here. Today what I'm going to be looking at, this is part 1, but what I'm going to be looking at today is a 4-channel mixer preamp. That is, we can take 4 separate inputs of any description, say guitar, microphone, CD player, line level, whatever, and mix 4 channels together into one and get a resultant output. Basically, this is our block diagram of the front end of the mixer, and these are all the potentiometers, the 4 of them, for each of the channels respectively, and each channel has its own separate input preamplifier. Now, by changing the feedback and gain structures of each of these preamps, we can get various different amplification ratios there for different types of devices such as microphones and guitars, etc. And for line input you would probably have very little to no gain, so unity gain basically on one of those channels. But we leave the preamplifier there so it can be versatile to be changed to whatever we want. So that's the basic rundown on what that is, and each of these are mixed through these pots via these wiper resistors into this inverting, what's known as a summing amplifier, which means it sums all of these inputs together, and the gain would be calculated between these resistors here. And what we'll be looking for here is a gain of about -2. Now each input, this is what's going to be the interesting thing. So if we take, for instance, an input signal of 50 millivolt from a electric guitar, they do output various different levels, but we'll just say for the sake of argument it's 50 millivolt at the input. We want each of these outputs to be the same. That is, the ratio that it amplifies its input to its output has to be the same on each of these channels. So for 50 millivolts, say, we'd want around about probably 2 volt peak to peak on its output. The same here. And if you're going to run, say, a CD player is very capable of producing close to 2 volt peak to peak. So all we'd need is a unity gain buffer there, because we'd have 2 volt here and 2 volt there. So that's where I'm going to ballpark the amplification gain structure of all of these preamps, is whatever the input is, we get 2 out. I mean, of course, this is in a perfect world. In the real world, guitars are not going to be 50 millivolt inputs all the time. The same as microphones are not going to be 3 millivolt input all the time. They're going to vary with the signal, obviously, but for the sake of argument, we're going to say 50 millivolt in will equal 2 volt out. And as I said, we need a gain roughly of -2 on here, so we're probably looking at, if I make all of these resistors around 47k, to get that gain of -2, roughly, it'd be about -2.1, we'd need a 100k feedback resistor here on this summing amplifier. So I'll just write in, for reference, what those values are going to be, albeit that's as messy as anything, but you get the point. So, and these pots don't have to be very high impedance. You can use 10k logarithmic pots here, because we've already really got a low impedance source before it, which is each of these preamplifiers. Because an op amp has a high impedance input versus a low impedance output. So we can get away with a 10k logarithmic pot here. And then, yeah, we mix them all together, sum it up, sum each of these outputs up to 1. I can't even speak. And then have an output at the end of this string here. Now, I'm going to be using any 5532 op amp ICs because they're fairly low noise and they're relatively cheap. I think the unit cost of one of them is like about $1.30. They're not that expensive. If I wanted to go ultra low noise, well, I could use an OPA dual channel op amp. I can't think of the number offhand, but it starts with OPA, and that's an ultra low noise and ultra low distortion op amp. But for purpose of what I'm using it for, I don't see the point. So what I'm going to do is I'm going to draw up on a piece of paper this better as a schematic so we can actually see some circuit values and, well, component values rather than circuit values. Okay, and here's my crudely drawn schematic. This shows our input preamp before each of these volume controls or mixing controls. And down here it says next channel. That just means it's a duplicate of this. So for simplicity, I've just shown the one channel, and we can assume that the next 3, or however many channels you actually want to add, it's limitless. It's really only limited by the current of the power supply, is identical to this stage here. So we've got our standard non-inverting op amp stage here. We've got a couple of resistors here setting the input impedance. We've got our main gain control resistor, which is going to be permanently fixed at 1K5, plus a 22 microfarad. In this case it's shown as an electrolytic, but in the final design I'll probably use bipolar. We have RF and CF. Now ignore the capacitor there for a second. This resistor feedback here is what's going to be varied for the different level of input sensitivity to give us an output approximately of 2 volt peak to peak. Okay, and CF is just put across this feedback resistor here just to ensure stability of the op amp stage. So its value is not overly that critical, but we want to keep it in the picofarad range so we're not interfering too much with the overall frequency response of this amplifier, because if you start using higher values of capacitance such as 10 nanofarad, 100 nanofarad, 220 nanofarad, such things like that, you're really going to severely change the frequency response of this op amp, and you could end up actually cutting the highs. So that's not what we want to do. So we've got a couple of bypass caps here for DC blocking. They're just standard 1 microfarad polyester, going into our 10k mixing pot for that channel, going through this 47k resistor, which is the mixing resistor, and there's another one down here as previously stated, then goes through this second blocking capacitor into this inverting op amp stage. This is the summing or mixing amp stage, and that sums all the inputs together into one, hence why it's called a summer or a summing amplifier. Its gain's fixed at 2.1 roughly, minus 2.1 by this 47k resistor and this 100k resistor here as the feedback resistor. And again, there's a capacitor across it of 22 picofarad just to ensure stability of the op amp here so it doesn't go into self-oscillation or anything stupid like that. It then finally goes through this blocking capacitor here on the output before going out to either the next stage, being a tone control stage, or just straight out to the power amplifier. Now remember, we're going to have our signal coming in like that, so that's non-inverted. Here it's also going to be non-inverted but larger, but here it's going to be inverted and slightly larger. So we've got to remember that it's going to be 180 degrees out of phase on the output here. Now if I was going through an active band axle circuit, which I will be for using tone controls, the signal then will be corrected back around 180 degrees, so it's back in phase with what the original input was. So if I wanted to put this out into a balanced line out preamp so that it can come out as a balanced signal, I've got to make sure that the signal is 0 degrees out of phase with the original input so that that balanced circuitry works correctly. Otherwise, being out of 180 degrees out of phase, well, we're going to have a 180 degree signal on the hot and a 0 degree signal on the cold, which would be, probably won't make that much difference to it, but it is back to front. So that's something to keep in mind. So what I'm going to do is I'm going to breadboard this all up, but see, the thing is we've got to work out the values of these resistors and capacitors. So down here I've made up a little table for what the input is, being electric guitar, CD player, line, microphone. I can add more if I want. We've got RN, RZ, RF and CF. So we've got RN, RZ, that's supposed to be a Z, not a 2, RF and CF respectively. So these values will be worked out given that we know roughly what the voltage is going to be at the input. Say for an electric guitar 50 millivolt. I didn't leave room to write that voltage, so I'll just draw up the table extended over here and put V in so we know what the voltage in is. So that's going to be 50 millivolt. There goes my alarm. Now 2 volt microphone 3 millivolt roughly. And then we'll just fill in the values by working out what the resistive feedback should be and what these values should be, etc. And you'll probably find most of the RN and RZ values are going to be roughly the same. And technically they should really be, but it really depends on the impedance of the input as well. So we'll have a look at that on some breadboard and play around with it. Okay, I've got everything set up. I'll just hook the DDS back up to the circuit. I've already tried it. All I've built is the input stage. Now I'm working on the 50 millivolt input range. Unfortunately my DDS doesn't have very good resolution and can't go down that low, and even at 100 millivolt in I am seeing quite a bit of noise on the output. Of course, as you increase the input sensitivity, the more clearer the signal gets. Anyhow, I've got 100 millivolt 1 kilohertz, 15 plus minus on the power supply, turn on the load, and we can see we've got a rather noisy output. So as you can see, for 100 millivolt in, we've got roughly 2 volt out, which is a gain of roughly 20. Which is probably more than adequate for what I need. So for the rest of the channels, that's what I've got to work around. Okay, so I haven't built the summing stage up yet, or any of the mixing stage section, but I was just trying to get the input stage squared away so I could work out some values. I'm not 100% there yet. I was just testing 50 millivolt. I'm still going to play around with it a little bit more. I'm going to work on the 2 volt input now, and we'll come back when I've actually got, I'm going to build up that 2 volt section on the other side of this op amp, and we're going to come back when I've done that and have a look at some differences in results. Because really what we want is the same output voltage on both channels, roughly. Okay, I'll have to delete all that shit because it's just bullshit. Okay, now I've got the second channel built up after I got myself confused. I just had the gain resistor across the wrong pins. I've got, I did stick a 680 in there and it got red hot, but I've got 1K5 to 1K5, so the feedback resistor is 1K5 and the gain resistor is 1K5 respectively. That gives us a gain of 2. So for an input signal of 2 volt, which is going to be our CD/line input, we're going to get 4 volt out. However, on the other channel, we've got a gain of only 2. So I need to double that resistance from 22k to about 47k, and that should give me an output voltage of 4 volt at 100 millivolt in. So I need to go from the output pin, which is pin 1, to pin 2, which is the negative terminal, and we have bugger all output. That's because the resistor's shorting. Now we've got an output voltage of roughly 4 volt, which is what we want. Now the resolution of my DDS isn't very good, so we'll change that to 100 millivolt, which is average enough. RN's 1 meg, RZ is 1 meg. That just gives us roughly an input impedance of about 500k. Resistive feedback's going to be 47k, and I've ballparked the capacitance feedback of 100 picofarad. For the CD line input, I've got 2K2 as an input resistor. The second impedance resistor is 100k. The resistive feedback is 1K5, and we're using 18 picofarad as the feedback. Okay, so now what I've got is I've got the summing amplifier connected up via two 47k mixing resistors. As I said, I'm only going to do 2 channels in this demonstration. The final will have 4. But I've yet to work out the microphone. I'll do that later. But first I thought, well, let's actually get some mixing going on. Now there's no pot connected between the output of the input preamp and the summing amplifier on either channel, and I've only just got one connected for demonstration. The output of the oscilloscope's been moved to the output of the summing amplifier. The summing amplifier is set to a gain of -2, so we should have a 180 degrees inverted signal. So if there was 4 volt at the output, we should now have a gain of 8. Well, we have an output, but it looks like absolute shit. I know why, because I forgot to connect the ground wire from the op amp to ground, which is pin 3, which is the positive input. The force of habit, I guess. So pin 3 to the ground plane. That fixed the problem. That looks a little bit healthier, and it is outputting 8 volt. So we change that to a trigger of 2 volt. We've got 8.27 volt peak to peak out. So it's about a gain of 2.2, which is about right. So we can see that the preamp itself, after mixing, because the reason we use an amplifier after mixing is obviously to make up the losses in mixing. So after mixing, we're going to have a gain of 8. That's with all controls set to full. That's assuming our input stage is 4 volt. So just to make things clear, we're going to change that to 4 volt peak to peak, and we're going to make that 8.2 volt peak to peak, so we know where we're going. Now that's still on the 100 millivolt input. Now if I switch the output over to the other channel and switch the input, it's going to distort because well, it's not going to distort because it's not loud enough. So if I change the amplitude of that back to 2 volt, again we have 8.5 roughly, so it's about the same. Okay, so even though that signal looks like absolute shit, my DDS is now down at 3 millivolts, so we're right down at the noise floor of the DDS. I'm trying to work out the microphone here, and I've got 4.7 coming out of the mixing stage, which isn't enough. It needs to be closer to 8. But I'm getting close. So I just doubled the feedback resistor there in the input stage, and I've got close to 8 coming out, including through the mixer itself. So that's about right. Got 470k feedback resistor, 10k input impedance resistor at the input of the op amp, and a 680 ohm on the other side of the input where the actual input's connected to the capacitor. So that's actually going across the microphone. For a 3 millivolt input, peak to peak, and a 15 picofarad feedback capacitor. And we're getting, albeit it's noisy as hell, we're getting about 8 volt peak to peak out, including through the summing amplifier. So that's all well and good. I suppose now I should hook up a microphone to that input and just see what it does on the oscilloscope. Okay, I've got an input socket there with a microphone cable going to it. You should use a switched socket so that you can bring the input when it's not used to ground, so you're not picking up so much noise in the circuit. That's connected to just one of these dynamic microphones, unidirectionals. I'm not sure what the impedance of this is, I'll measure it after. So with the microphone not really any more than 2 feet away from me, we can still just see that the oscilloscope is moving when I talk. If I bring the microphone up to my mouth where it normally would be, we can see that it is amplifying the signal, and we're getting about 5 volt peak to peak out, which is okay, average. I mean, microphones are always going to be lower than your input source, but I could also have the input impedance incorrect. So what I should do is measure what the actual input the impedance of this microphone is. So the impedance of that microphone is about 556 ohm. I would say that that would be a fairly high impedance microphone. So I've probably got the wrong resistor there at the input. So I've got 680 for low impedance. High impedance of that impedance should be about 1 meg. So with our 1 mega ohm input resistor in place of R in, we're getting closer to 8.5 out of the entire circuit. So yeah, I'm not sure if that's going to make a difference to our microphone. Hello, hello. Oh yeah, we seem to have a larger output swing now. Yeah, it's more like 12 volts. So yes, that R in resistor, especially for microphones, is rather important. So we've almost doubled or tripled our output from this microphone. So I now know what the two types are. So I know this video is getting long. I can't help that, sorry. So I'm going to put that as low Z and add in microphone high Z. So our input resistor is 1 meg, and our op amp resistor should actually be more closer to 100k than 10k. I'll test that again in a minute. I'm leaving our feedback capacitor to 15 picofarad. Well, that resistor didn't even make contact where it was supposed to be. It's supposed to be there, so I bucketed that up for a start. So we'll change that to 100k there. I'm just pulling values out of my ass right now. Well, that's a little bit better. Yeah, that's a lot better. We've actually got quite a higher output. We've got 22 volt there. Yeah, 22, 27. Whereas we had, I can't remember now that looking back at the footage, but we had a lot lower. So if I now connect the DDS in place of the microphone, let's see what our output voltage swing is. Because we want to keep it to 8 volt, if we can. So I connect up that. Yeah, we're closer to 9 volt. I'm going to leave it at that. So that needs to be 100k. And that's fine. And it should work fine. So we've got low Z microphones, high Z microphones. It's really up to you to do experimentation. Okay, so I got the two 10k pots wired across each channel now into the summing amplifier. The one on the left is for the line input side, and the one on the right is for my microphone at the moment, which I'll also change to guitar later in this video when I'm doing the sound test in just a few moments. Okay, so I'm going to rotate the microphone pot now. It's still connected to the DDS, and we can see the volume is changing when I rotate the pot, which is exactly what I want. So now I'll just turn the output off, well, the thing off, the circuit off. I'm going to hook it up to a power amp, and I'm just going to use one of those Class A modules because A, they're convenient, B, it'll run on 15 volt, which is what this circuit here is running on. It just won't be very loud, but it's, for all intents and purposes, it's not really important for the test. Okay, got the Class A amplifier hooked up. It's just going into that crap 15 ohm speaker on the floor. I've got the microphone hooked up to the microphone input. The volume of that is down, and there's no master volume yet, so it's probably going to be rather noisy on the output. Turn it on, hopefully it doesn't explode. No, I can't hear any noise. So I'll up the volume of, oh, there we go. Yeah, that's actually working quite well. There's a little bit of buzz. That's because of all the circuitry wiring here. But as we can hear, it's amplifying my voice, and it sounds rather nice. Penis. Oh yeah. Oh yeah. Laurie loves tires. Oh yeah. Anyway. So what I'm going to do is I'm going to hook up the other channel to, say, the CD player and play a track, and we're going to mix the two channels together and just see what it sounds like. So there we go. We're mixing two channels. Isn't that cool? But the microphone seems to be a bit louder for the volume setting of the mic compared to that. So, penis. A penis. Oh, penis. Oh, yeah. Oh, yeah. My penis is high. Okay, right. That seems to be functioning as it should. So, for high impedance microphones, I might just reduce the gain from 470 to 220k, just so we're not got so much gain there. So we just pause that, and I'll turn it off. Delve into the circuit, and what am I changing? I have no idea now. That's the 470k. So we take that out and we try 220 instead, just to see if it'll reduce the gain a bit, but we want to keep it roughly in line with the line input signal, so it's not doesn't have as much gain as it does at the moment. So it's really a toss-up. So we turn the power back on. I think I've not got any output now. Things are shorting. Okay, there we go, we got output. Now if I increase my volume a bit, that's probably a little bit better for the settings of the pots. So I'm going to leave it at that. And now I've got no input signal from the CD player anymore. Now I have. That's the problem with breadboard, things short. Well, apart from the distortion on the track, it sounds like track anyway. Change the track. Yeah, it sounds reasonable. It's working as a mixer, that's the whole entire point. I'll stop the CD player now. Talking through the that's distorted. Talking through the microphone, it's not too bad. It's sounding okay. So, what I'm going to do is I'm going to change my gain now again, so I can hook up a guitar to it instead of the microphone. Let's see what happens when I turn the microphone off. The noise goes away. Yeah, I'll hook it up to my bass guitar and we'll just have a little bit of a listen. Okay, turn the power back on. Probably a bit too much gain there. Drop the input down a bit. Yeah, okay, it sounds alright, but might be a little bit too much gain there for the guitar. Most of that rattling is coming from the speaker driver, and all that noise is coming from the power supply because the audio lead for the guitar is jammed under the power supply. It's not pulling off the desk, but yeah, it works. As I say, I might want to tame that gain just a tad on the guitar, because this is going on, that was only going on 100 millivolt by the way, and this guitar is quite capable of around about 400 millivolt peak to peak out. So yeah, you'd have to like work out the gain structure based on the output gain of your bass or your guitar, because they're all different depending on the style of pickups you've got. So that's something to play with, but it's just a basic basis at the moment of the concept to see that it works. So now I've plugged in the 5-string bass and there's a lot less gain there, so I'm going to have to increase the volume just a tad. gain. That's enough of that. I'm just going to turn that input right off. There we go, that gets rid of the noise. As I said, the noise is only being picked up by the circuit because of the layout and the fact that the audio input lead is jammed underneath the power supply. So anyway, I think I'm going to leave this video here. I'll just start the CD player going again. I'm going to leave this video here today. This is part one. This is basically the input stage, working out the gain and the mixing op-amp section. The next video I'll go into the, well, not so much the band axle, but the output stage that's needed to go to the power amp, because we're going to include a master volume control, which means our total output gain with all the tone controls in the middle or flat, probably looking about 12 volt peak to peak. So that's going to be it for this video. Thank you for watching, and if you enjoyed this video, please remember to rate, comment and subscribe below. You can always follow me on Facebook and Twitter. The links are in the description as usual. Anyway, this is the Astro 30 saying, see ya, have a great day.